Hello and welcome students. This is a lecture on vectors and right now we are into scalar triple product. I have already explained you the definition of scalar triple product. Then we have also solved number of problems on scalar triple product. Now we are going to start with volume of a parallelepiped and volume of a tetrahedron. These are two topics that we have to complete in this lecture: volume of a parallelepiped and volume of a tetrahedron. I will not do the theory part of it, that is, I will not do the derivation. In this lecture, I am not going to take the derivation. The derivation I will take in another lecture. Here, I am going to explain you how the formula is written for a parallelepiped, how the formula is written, what is the formula for volume of a parallelepiped and volume of a tetrahedron that arises from the three vectors. Okay. And why three vectors? Because it is triple product. Okay. See, one thing is very clear, that when you are going for the volume of parallelepiped, you are going after scalar triple product. You are going for it after scalar triple product. It means definitely scalar triple product is being used here. So volume of a parallelepiped is an application of scalar triple product. Okay. For getting the volume of a parallelepiped, we are going to use scalar triple product. So let's begin with the topic. See here. See here, I have three vectors A bar, B bar, and C bar. Okay. So here we have three vectors A bar. We have three vectors A bar, B bar, C bar. Okay. And these three vectors A bar, B bar, C bar are coterminous edges. They are coterminous edges of a parallelepiped. They are coterminous edges of a parallelepiped. Okay. Now, what does that mean? You all understand the meaning of coterminous. Coterminous is having common terminal. Coterminous is having common terminal. For example, suppose here I have a vector. Okay. Then here I have another vector. Another vector. Then I have one more vector. See, these three vectors are coterminous. Why? Because they all are arising from the same terminal. Okay, they are all arising from the same terminal. If I call this as A bar, this is B bar, and this is C bar. So what do you notice? Vector A bar has initial point here. This is initial point, say O, and the terminal point is A. Vector B bar has the same initial point O, and this is terminal point B, and here it is terminal point C. They all have the same initial point. They are coterminous. They are coterminous. Okay. So what am I given? I'm given that A bar, B bar, C bar are coterminous edges of a parallelepiped. So first of all, what I will do is, let me draw a parallelepiped for you all. Okay, so let me draw a parallelepiped for you all. So I will begin with a parallelepiped. First of all, see, here I have one of the edge. This is one of the edge of parallelepiped. Then this is another edge. So you have three vectors here, and they are coterminous edges of the parallelepiped. So let me have, there are three, these are the three vectors. So let me have O here, and this is A here. So this is vector OA bar. What is this? This is vector OA bar. Okay, I call it as A bar. Let me have point B here. So this is point B. This is vector OB bar. This is vector OB bar, which I call it as B bar. And then here, this one is O, and this point, let the extreme point be C. This is vector OC bar, which I call it as C bar. Now, these three vectors which you see here, they are the coterminous edges of the parallelepiped. Okay, they are coterminous edges of the parallelepiped. Now, but where is the parallelepiped? Do not worry, it will now come. It will now come. See, these are the three vectors, and now I'm going to get you the parallelepiped. See, students, the parallelepiped, the base is a parallelogram. So here, first of all, you will have a parallelogram. See, let me complete the base parallelogram. Okay. The base is a parallelogram. So I got the base here. Now, see, like in a cuboid, what you see, the base is a rectangle. When you draw a cuboid, what you have, the base is a rectangle. In a parallelepiped, the base is a parallelogram. In a cube, what is base? In a cube, the base is a square. The base is a square in a cube. Here, the base is a parallelogram. So first I drew the base parallelogram. See, this is a parallelepiped that you have. You got a parallelepiped. And for this parallelepiped, what you see the coterminous edges. The coterminous edges are A bar, B bar, C bar. You know these three edges. Okay. This part is the base of the parallelepiped. See, here you have, this is the base of the parallelepiped. This is base, which is a parallelogram. You see this? This is base of the parallelepiped, which is the parallelogram. A parallelepiped is a 3D object. See, this is base. And here, this one is this is the top of the parallelogram. See the topmost surface, the upper surface, the top. Okay, this is the top of the parallelepiped. Okay, and here these are, see, so up there will be total 6 faces. See, this is the bottom one. Okay, 1, 2, and then you have 4 sides. Okay, the faces to the side. See, this is one side. See this? This is to the right extreme. Then from here, then from here you will have one that is to the left. That is to the left. Then this one is the front one. Then you will have one from the front one. See, this is the front one. This is the front one. And then you have the last one that is from the back side. So the last one is from the back side. See this from here. So total 6 faces are there of a parallelepiped, just like a cuboid and cube. But there in cuboid and cube, the edges, the vertical edges are all perpendicular to the horizontal surface. They're all perpendicular, but here it is not perpendicular. In cuboid and cube, what you have, the edges are perpendicular. In cuboid and cube, what you have is the edges are perpendicular. The vertical edges are perpendicular in cuboid and cube. See, this is this is a this is a cube. Sorry, this is a cuboid. So here what you notice, you can check. See, these vertical edges are perpendicular. You can check. See, these vertical edges all are perpendicular. You see this? See, the vertical edges are perpendicular to the surface. Look at these angles. These angles are all 90-degree angles. You check this. These angles are all 90-degree angles. But here it is not the case. This is parallelepiped. See, these all angles are not 90 degree. They are not 90-degree angle. You check this, they are not 90 degree. But here all are 90 degree. I hope you understand. So we have a parallelepiped. So the parallelepiped that you have, you don't have to shade all this. You don't have to do the shading. Okay, you just have to draw the diagram like this. So see here, you have OA, B, C. So I write here OA. See this one, I write P. I write here P. P. This point I write Q. This I write R. And here I write S. P, Q, R, S. Okay. So this is parallelepiped, and the coterminous edges are A bar, B bar, C bar. Okay. Then you can write the volume of the parallelepiped. The volume of parallelepiped is equal to box product of A bar, B bar, C bar. Yes, that is it. You know, what is volume of this parallelepiped? It is equal to box product of A bar, B bar, C bar. The box product of A bar, B bar, C bar is the volume of the parallelepiped. Why? And when this is true, when it is true only when A bar, B bar, C bar are the coterminous edges of the parallelepiped. Coterminous edges, they should be coterminous edges. Okay. For example, suppose this vector you have M bar, but that, okay, this vector is N bar, M bar, N bar, and this vector is R bar. So are these vector coterminous edges? No, they are not coterminous edges. They are not coterminous. When you have coterminous edges, then only you can write the volume like this. Please, you can copy this. Now we are going for the volume of a tetrahedron. Let us go for volume of a tetrahedron. So what is a tetrahedron? First of all, I'll get you that. See here, as the name suggests, it is a tetrahedron. So there are going to be 4 surfaces. Okay. And we have 3 vectors. Once again, we have 3 vectors. See, A bar, B bar, C bar are coterminous. They are coterminous edges of a tetrahedron. They are coterminous edges of a tetrahedron. So I will first go for, see, I will go for vector A bar. Okay, then I go for another vector B bar. I go for another vector B bar, and then I go for the third vector, that is C bar. Okay. So see, these are three coterminous edges of the tetrahedron. So here this point, they are coterminous. They are coterminous edges. So they all are originating from point O. You know, they have the coterminal. That is, this is same initial point. This is I will write it as C. So I got this as OC bar, which is C bar. Then I'll write this as A. So I've got OA bar, which I write it as A bar. And here I have point B, which I write it as OB bar, which is B bar. So I have three coterminous vectors. Now I will complete the tetrahedron. See, for completing the tetrahedron, the first thing I will do is the base is a triangle. Remember, the base is a triangle. Okay. The base is a triangle. The tetrahedron has four surfaces, and all the four surfaces are triangle. So this is base triangle. Okay, and then here you have, see, this is the apex. C is the apex. Now you have a tetrahedron. Okay. See, I will show it to you. I will try to show the 3D 3D view of this, and see, for that, you know, this is base. Triangle OAB is the base of the tetrahedron. It is the base of the tetrahedron. So let me first cover the base. See, this is base of the tetrahedron. This is base. Base surface. It is the base surface. It is the surface on which the tetrahedron is resting. It is resting on this. And then see, from here you have, see, this one, this surface is the one that you have on the right side. See, ABC, triangle ABC, this surface, you see this surface, triangle ABC, it is the side surface, the triangle, the side triangular surface. And then here you have the front triangular surface, OAC, triangle OAC. And this is from the back side, see, triangle OBC, triangle OBC, it is from the back side, this surface. So the side surface is this one. This is the side surface. This surface you have is the side surface. This surface is the side surface. It is a tetrahedron having three coterminous edges. Three coterminous edges. You don't have to provide any shading to the diagram. You just have to understand. Now, volume of this, once again, this is a 3D object, 3D geometry. Okay. The volume of this tetrahedron is given by volume, and right here, the volume of tetrahedron. The volume of tetrahedron is equal to box product A bar, B bar, C bar, like it was for the parallelepiped. In the parallelepiped, you had written box product C, you had written A bar, B bar, C bar, when the three edges were A bar, B bar, C bar. Here also you have three edges A bar, B bar, C bar, so you will write box product, but you will also multiply 1 by 6. Remember, it is 1 upon 6 times box product of A bar, B bar, C bar. You will multiply 1 by 6. Okay. If you do not multiply 1 by 6, then what will happen? Then the value which you will get, it will be the corresponding parallelepiped. Then it won't be the tetrahedron. If I do not multiply this 1 by 6 here, suppose I do not multiply 1 by 6, and I calculate A bar, B bar, C bar, the box product, what I will get, then I will get the volume of the corresponding parallelepiped. I will get the volume of the corresponding parallelepiped where A bar, B bar, C bar are the coterminous edges. That is this thing I will get. See, suppose I now extend this, you will understand it. See, now I'll extend this. See this. You will get the volume of this parallelepiped. In the same diagram, you have a parallelepiped. You will get the volume of this parallelepiped. If you do not multiply 1 by 6, see, it has become a parallelepiped. It has become a parallelepiped. You have a parallelepiped with the same A bar, B bar, C bar as the coterminous edges. But what I did, I multiplied 1 by 6. When I multiply 1 by 6, what will happen? Then it will be the volume of the corresponding tetrahedron. It will be the volume of the corresponding tetrahedron. Okay. I hope you all followed it. Please, you can copy this now. Students, we have done two formula. One is for the parallelepiped, when you know the coterminous edges of a parallelepiped, and the another formula for the tetrahedron, when the coterminous edges are for the tetrahedron. See, these two formula can be derived. The derivation is very simple, but I will do that in another video. Right now, I'm not doing it. Otherwise, the video will become very theoretical. Okay, you can see the another video for the derivation. Now here I have a question based on the volume of a parallelepiped. See, they say if the vectors 3i cap plus 5k cap, 4i cap plus 2j cap minus 3k cap, 3i cap plus j cap plus 4k cap are coterminous edges of a parallelepiped. If these three vectors are coterminous edges, you already know what are coterminous edges. You can imagine them. So these three vectors are those coterminous vectors, and they are the edges of the parallelepiped. They say, then find the volume of the parallelepiped. Then find the volume of the parallelepiped. So see, how do I begin? See, if this question is a MCQ type of question, then you don't have to do anything. You just have to find, the scalar triple product of these three vectors. That is, you will put them in a determinant. You will write 3, 0, 5 for the first one. Then you write 4, 2, minus 3 for the second one, and 3, 1, 4 for the third one, and then calculate whatever you get. Cubic units is the answer. Whatever you get, that those many cubic units is the answer. Okay, but here, it is not. If you're writing the answer in detail for suppose your board exams or something, then you will have to write like this. You write, let A bar be the first vector 3i cap plus 5k cap. Okay, then B bar be the second vector, which is 4i cap plus 2j cap minus 3k cap, and C bar will be the third vector, that is 3i cap plus j cap minus plus 4k cap. Okay, now you will write volume of parallelepiped. You will write volume of parallelepiped is equal to box product A bar, B bar, C bar. And then you will write the determinant which I spoke about. Okay, now you'll write the coefficients of I cap, J cap, K cap for the vector A bar, B bar, C bar. So here for A bar, it is 3, 0, and 5. There is no J cap here. So 3, 0, 5. You have 4, 2, minus 3. You have 3, 1, and 4. Now you calculate this, you'll get the answer. Those many cubic unit is the volume. So you have 3 into, now you evaluate the determinant. 3 into, you have 3 into 8 minus of minus 3, that is 8 plus 3. So 8 plus 3. Then you have minus 0 into whatever number you get, it is going to be 0. Okay. So 0 into, see, you have 16 plus 9, 16 plus 9. Okay, then you have plus 5 into 4 minus 6, 4 minus 6. So you got here, say this is 11, 33. This is 0, forget it. And this is -2, -10. So you got here 23 cubic units. You got here 23 cubic units. This is the volume of the parallelepiped. I hope you all followed it. So after doing the volume of a parallelepiped, now we are having a question where we have to find the volume of a tetrahedron. But in this question, there is a slight difference, and it is they are not giving us the three coterminous edges. See, in this question, they are not giving us the three coterminous edges. Instead of that, what they are giving us is the four vertices of the tetrahedron. Yes, they have given us the four vertices of the tetrahedron. So these are three coterminous edges. They are not giving us the coterminous edges. No. They are not giving us the three coterminous edges in the form of vector. So suppose this is O, this is A, okay, this is B, and this is C. These are the four vertices of the tetrahedron. These are the four vertices. What we are given is the coordinates of these vertices. We can always complete the tetrahedron. See, I will join this with this here, then I'll join this two, and I'll join this. See, now I have the tetrahedron. I have the tetrahedron. Are they giving us OA bar, OB bar, OC bar? No, they haven't given us that. So what are they giving? See, instead of O, let me write here D. They have given us this D. Okay. So what I will have to do in order to find the volume of the parallelepiped, I'll have to find these three vectors. I need vectors, I'll have to find these three vectors. Which three vectors? dA bar, dB bar, and DC bar. I'll have to find dA bar, dB bar, and DC bar. Once I get these three vectors, then I can say that I will find out the volume of the tetrahedron. Now see, it is all up to you students. It is all about the naming, Don't worry about the naming. It is not that the common vertex has to be, the coterminous point has to be D. Nothing like that. See, if you want to write it here, A, B, C, D, you can do it that way also. So if you do it this way, it will be termed as AB bar, AC bar, AD bar. I know you prefer this way, AB bar, AC bar, AD bar. So you can write like that. So here I will begin with the answer. So, as such, the diagram is not necessary, but for the sake of explanation, I have drawn the diagram. This is the surface from the side, this is the side surface, which is also a triangle. This is also a triangle. From this side. So here now I have, see what I will write. I'll write here the position vectors, of points A bar, B bar, C bar, and D bar are given as, see now I'll write A bar. What is A bar? A bar is minus I cap plus 2j cap plus 3k cap, minus I cap plus 2j cap plus 3k cap. B bar is 3I cap minus 2j cap plus k cap. C bar is 2I cap plus j cap plus 3k cap, and D bar is equal to minus I cap minus 2j cap plus 4k cap. Now I will go for the Vectors here, see, I will go for AB bar. I'll write here. AB bar is, what is AB bar? AB bar is B bar minus A bar. It is B bar minus A bar. This is AB bar. So what is B bar? B bar minus A bar. So see here, 3I cap minus of minus I cap. So this will become 4I cap. Then minus 2J cap minus of 2J cap. See, this is B bar minus A bar. So when you will do minus A bar, you understand all these terms will change their sign, you know. So minus 2J cap minus 2J cap will become minus 4J cap, minus 4J cap. And then here you have K cap minus 3K cap, which is minus 2K cap. This is AB bar. This is, so you got one of the edge, you got one of the edges AB bar. Now I'll go for AC bar. What you will write for AC bar? See, AC bar will be, you will write now, AC bar is, as you know, C bar minus A bar. So C bar minus A bar. 2I cap minus of minus I cap, that is 3I cap. Then you have J cap, C bar minus A bar. So J cap minus 2J cap is minus J cap. Then 3K cap minus 3K cap is 0K cap. Even if you don't write 0, it is okay. So you got AC bar. So you got the another edge. You got this edge. Now you got this edge. We go for the next. Now after that, we will get AD bar, the vector AD bar. What is AD bar? It is D bar minus A bar. So see, the vector AD bar, you will get as D bar minus A bar. So minus I cap minus of minus I cap. So see, minus I cap plus I cap, it will become 0 I cap. Okay, then minus 2J cap minus of 2J cap, that is minus 4J cap. Okay, see, it is minus A bar. So all the signs here are changing. Okay, then you have 4K cap minus 3K cap, that is equal to plus K cap. You got a single K cap. Okay, so now you have all the three coterminous edges. See, you have all the three coterminous edges here with you. See, this is one of the coterminous edge. This is the other coterminous edge. And here the third coterminous edge. You have all the three coterminous edges. Now I can write the formula for the volume of parallelepiped. I can write the formula for volume of parallelepiped. I will write here volume, therefore volume of, I'm sorry, I said parallelepiped, it is tetrahedron. Okay, so volume of tetrahedron is equal to 1 upon 6, and see, the coterminous edges are, so you will write AB bar, AC bar, and AD bar. Now see, this 1 upon 6 will remain outside, and for the box product of these three vectors, you will use the determinant. So AB bar is 4I cap minus 4J cap minus 2K cap. So you'll write 4 minus 2. And here for AC bar, you will write 3 minus 1, 0. And for AD bar, you will write 0, minus 4, and 1. You'll calculate this 1 upon 6. And then say this is 4 into, you know, minus 1 minus 0, that is, then plus 4 into this, and this is gone. You get 3 minus 0. You get 3 minus 0, and then minus 2 into minus 12 minus 0. What do you get? You get minus 12. 3 into minus 4 is minus 12, minus 0 into minus 1 is 0. So you get here 1 upon 6 times, see, this is 4 into minus 1 is minus 4, plus 12 plus 24 plus 24. So this is plus 12 plus 8. So this is okay, plus 24. So how much you get? This is here you get minus 4 plus 12 is 8, 32 upon 6. You get 32 over 6, that is equal to 16 over 3 cubic units. Cubic units is the volume of the corresponding tetrahedron. I hope you all followed it. You can copy this.